Well, as I did with the last module, I want to make a brief presentation about one of the key concepts for this module, and that is randomness in simulation models. You know that one of the other concepts from this module is queuing. There's an extensive lecture video that is included with this module, and I would encourage you to watch that. I think that it covers the topic of queuing very thoroughly. And so my focus for this presentation is going to be on the topic of randomness, random inputs in simulation models. So we learned in Module 1 that a simulation model is just a representation of a system. And it is impossible to replicate all of the details of a system, but the key details are replicated as accurately as possible so that we can make decisions based on the simulation model, decisions for the real system. Remember that the purpose behind simulation is to be able to study systems easily, safely, and economically in order to make changes to those systems, such as the addition of machines, such as the reorganization of the flow of product or flow of people through a system. So we're looking at the inputs and the outputs of a system, and randomness really here is looking at the inputs of the system. You may have read as you look through the resources for the week that discrete event simulation models are stochastic. This simply means that some of the inputs are based on statistical probabilities. Now, if you think about this a little bit, you know that some inputs are constant. They're expected. We know what they are. For example, if a production line gets a delivery from a supplier at the same time each week and a known quantity is delivered, that would be an input that is known. It is not variable. It is not random. However, we do have random processes in systems, and these would include things like waiting times, service times, times between arrivals of customers, times between machine breakdowns. All of these random processes have to be replicated in some way in a simulation model. This is the challenge of creating a simulation model that is valid, that accurately reflects the physical system that is being modeled. So you may recall in Module 1 that I showed a diagram that showed a single input going into a system and then a single output coming from the system. Those outputs help us to make decisions, and we'll be looking at that concept in a future presentation. But this week we're going to be looking at inputs, and instead of a single input, you know now that there can be multiple inputs going into a system in order for it to function correctly. So those random inputs go into the system where they change, and we end up with an output, or of course several outputs coming from the system from which we make decisions about the system. So those random inputs need to be modeled in some way, and the way that that is done is using typically a probability distribution. And so there are a couple of questions that need to be asked when creating a simulation model. The first is, what probability distributions should be used in a model? And then the second question is, how does simulation software generate random samples from probability distributions? There are two articles in particular that you should look at for this concept of randomness. The first is by Kelton, that was assigned to you. He talked about representing and generating uncertainty effectively. And then the second article that is recommended is by Avril Law, who is a well-known simulation practitioner, and he actually has created a piece of software called Expert Fit that looks at this exact issue of probability distributions in simulation models. First, let's take a look at the article by Kelton. So Kelton says that there are two components to a simulation model. There are the structural components and there are the quantitative components. The structural components are the ones that are fun to put in your model. And in the upcoming modules, when you create a simulation model using FlexSim software, you'll find that the structural parts of the model are really enjoyable to create. So this is things like putting people, operators, machine operators into the model, or selecting a piece of equipment for the model, or a conveyor, or a flow item, such as a product that's going through the simulation. Those things are relatively easy and enjoyable to implement in your model. But the second component is the quantitative component, and this is where the challenge lies, and this is what we're talking about today. The quantitative component of a model is saying how we look at making a reliable model using the correct quantitative components and not just the correct structural components. Kelton says there are two kinds of inputs, deterministic and random. I mentioned before deterministic inputs, things like deliveries that can be expected at the same time each week in the correct quantity. Others would be, for example, the number of machines in a model. We know these numbers. But then another kind of input would be the random inputs. And I've discussed what those are already. Not all of the inputs are independent of one another. Some can cause buildup and congestion in a system. For example, on page 41 of his article, he talks about that. And Kelton also cautions against using a normal distribution to reflect inputs in a model. So let's say that customers are arriving to a doctor's office. Someone may say, well, a normal distribution is common. Everybody knows a normal distribution. I think that a normal distribution is going to reflect how patients arrive. And Kelton cautions against this because, as you will see here, a normal distribution really has infinite tails in both the positive and negative directions. And while those numbers are very, very unlikely to come up, because of all the data that's used in a simulation, millions and millions of data points, it's possible that you're going to get one of those very negative or very positive numbers when you are selecting from a normal distribution. And so he cautions against using the normal distribution. Just to back up a little bit, the most common method for selecting a distribution for a random input is to take sample data from that actual system. So for example, let's talk about the time between machine breakdowns. Nowadays with computer systems the way they are, control PLCs and so on, controlling machines, it's possible to determine how much time elapses between breakdowns of a machine. This is the mean time between breakdowns, typically, the number is called. And someone could collect that data from a machine pretty easily. So if you were making a simulation model of a system, you could gather that data and then plot those times in a distribution and then say, what kind of standard distribution does this mirror most accurately? And then you can take that, fit the standard distribution to the input data, and then artificially generate more data based on the standard distribution. The problem with this is that there really are few standard distributions, and you may not find one that works, one that fits the data correctly. And so it's also pretty labor intensive to do this for every single random input in your system. An example of another standard distribution that is often used instead of the normal distribution is called the Weibull distribution. And you'll see that it does not have the infinite tails in both directions. It has different shapes, but it's kind of similar to a normal distribution with the exception that it does not have those infinite tails. You'll see as we create some simple models with simulation software that the Weibull distribution is used pretty often. Some others would be a triangular distribution, an exponential distribution, and there are others, and these can just be selected when you're creating your model. So let's back up a little bit and think about if you have an item in your simulation and you have to select a random data input for that. What are the methods for selecting that input? Well, the first is to use the actual sample data. So as I said, it's pretty easy to collect data from a machine nowadays, and manufacturers produce lots and lots of data about their processes. So you could actually use the sample data and then just feed it into the system and use that data. The problem with this is that you're going to exhaust your data really quickly. You may have thousands and thousands of data points or even millions, but because of the way computers work and how quickly they process information, a simulation model is generally going to exhaust actual sample data really quickly. And so you won't have enough data for your model. The second method for selecting random data inputs, and this is probably this is the most common method, and I just described this, as you fit your sample data to a standard distribution. And as I said, the problem with this is there really are only a few standard distributions, and so these may not work. Also, it can be labor intensive to get sample data for every random input in your system and find a suitable standard distribution for that input. The third method, and the method that Kelton suggests, is kind of a middle-of-the-road approach. He says to specify an empirical distribution. So in other words, you make a histogram plot of the data that you get from your system and then generate data based on that distribution. So you're really making your own distribution here. This is not going to be dependent on fitting the data to a standard distribution, so you don't have to deal with that. And it's going to be quite accurate because you're using your actual sample data to make your histogram. So Kelton suggests this method for the most accurate random data input for the system. The next article by Avril Law talks about some of the pitfalls in selecting simulation input probability distributions. And I want to bring these to light because if you are using the most common method where you would fit your data to a standard distribution and then use that distribution to generate random numbers, this is something you'll need to think about. So the first pitfall is just replacing a distribution by its mean. So as Law explains on page 1396 of his article, if you replace a random variable with a constant distribution mean, that's an error because the system can become congested, and that mean will misrepresent the random numbers that should be replacing it. So he cautions against this. The second pitfall is simply using the wrong distribution. So in a nutshell, we talked just previously about the normal distribution and how it's seldom appropriate due to its infinite positive and negative tails. But similarly, you could choose another incorrect distribution and end up with a wildly inaccurate input. And he describes in his article in a series of steps how to determine the best distribution that's going to represent the data. Many simulation software packages have expert fit software, which allows you to feed in sample data and then it just chooses the right distribution. So this is really desirable. Something else I want to talk about just briefly, because I neglected to talk about this when I talked about the Kelton article, but Kelton talks about random number generators, and random number generators, or they're sometimes called pseudo-random number generators, are typically going to be built into your simulation software package. You may know that Microsoft Excel has a random number generator. You can just type in random and parentheses and it will give you a random number between 0 and 1. But a good random number generator is going to be a long period generator so that the numbers don't start recycling until you get until 10 to the 60th is recommended by Kelton. So if you are a simulation practitioner or managing a simulation project and you're using a piece of software, you'll need to ensure that the random number generator in the software is a good one. That is, it has a long period to its random number generation. Kelton also talks about having different streams in the random number generator. These are going to be necessary because you have different random inputs in your system. Remember that you're not going to have just a single random variable in your simulation. You're going to have several streams, several inputs that are random, and so that random number generator has to be multi-stream in order to be accurate. And if you haven't read the Kelton and Law articles prior to watching this video, you may be struggling a little bit to follow the concepts. Please go ahead and read those articles and write down some notes as you read them, because that's going to be essential to understanding these concepts. I just want to close with a slide just called expectations, because you may be feeling overwhelmed at this point with selecting random number generators, understanding the probability distributions. And so I just want to kind of give you a brief overview and kind of a point of view that you should have as you read these articles. Do I expect you to be able to take a series of data and then select an appropriate distribution? Not necessarily. However, if you're going to be in a position where you're overseeing a simulation project and you're working with a simulation practitioner, you should be able to intelligently dialogue regarding how random numbers are selected. For example, if you're told that a normal distribution will be used to select a random number stream, that should be a red flag to you. And so it's important for you to understand the criteria for selecting those random numbers in a system and understanding the concept of randomness within a simulation system. If you have any questions, please post those to the discussion board. I look forward to answering those, and I hope this has clarified some of the concepts for Module 2.